paper for this lesson because I've realized I've been working digitally for the other lessons, and it looks like we might need to do some drawing.
Yeah, but not imminently. Maybe if you've got a piece of squared paper, that'll make your life easier, or graph paper, but not essential right now.
Okay.
Morning, everybody. Right, guys, let's make a start. I think some people have got an exam this morning. Cool. I've got a fancy register taking thing now. Cool. Right, hopefully everyone can see. So this is our new topic, but it kind of follows on from space a little bit because we're talking about lenses. So it kind of links with telescopes and things. So we've got a little bit of a link here to the last topic, right? We are starting partway through the chapter on pages 208, like it says in your assignment today. Just because the lenses stuff sits nicely as one chunk of this topic, and we've done some work on reflection and refraction already in earlier topics, right? So this list, and you've got to print out a doc of these diagrams and things if you want to use them, and then I'm going to share a printout of what my screen ends up looking like after we've had this meet at the end. So you'll have notes anyway if you want them, without doing anything other than listen now. So we've got some keywords here. They're kind of in pairs. So when we're talking about lenses can be concave or convex. Okay, think a cave goes inwards. There's a concave lens, and the opposite of concave is convex. Okay, so we've got two types of lenses, one that get narrower towards the middle and one that get fatter towards the middle. And those match up with these two words here, converging and diverging. Okay, so a convex lens is a converging lens, and converging means bringing to a point. So if we go into, and some of you will have done this already when we looked at light before, if we took our convex lens and we shone light through it, then the lens would have the effect of bringing that light to a point like this. Okay, we'd say there's a principal focus for this lens. So converging to bring to a point, and obviously diverging is the opposite of that. And so a concave lens with its caves on either side is going to do the opposite. It takes light, and the light spreads out like this, and we should show the direction of these rays of light here. We think of this diverging lens as having a focus as if these rays of light come back to a point here, okay? So it's behind the lens from where the light has come from. Okay, next words. When you're describing an image that forms, so obviously we use lenses to make images. It might be that we're projecting an image onto a wall, like with a projector in a cinema, for example, or it might be that we're making an image that we're looking at like in a magnifying glass. And those two examples define these words here. So if an image that forms is real, it means we can project that image onto a screen. It means that the image has rays of light that pass through it. You'll see what that means in a minute. A virtual is the opposite of that. A virtual image cannot be projected. No light is going to pass through where the image forms. So, for example, the image in a mirror is virtual. When you look into a mirror, you're seeing an image, but there's no light behind the mirror. So we say that it is virtual. You cannot project that image from a mirror onto a screen. Okay, next pair. An image can be upright or inverted, and that's easy. Upright means it's the right way up, and inverted means it's upside down. Okay, so for example, if you've ever looked through a telescope, most telescopes form an inverted image. You see something magnified through the telescope, but it's upside down. Next to. Again, simple words. Magnification is how much bigger than real life it is. So magnification is more than a magnification of 1 or bigger. And diminished is less than a magnification of 1 and is smaller. We'll see how we calculate that in a minute. And finally, we've got two keywords here that refer to lenses. The focal length is the distance between the center of the lens and the principal focus. So this would be the focal length. And the primary axis would be this line that goes through the center of the lens that's horizontal. Okay, and we can make measurements relative to that. If we were in school, we'd be doing some experiments with ray boxes and looking at lenses, and we'd see that we could take convex lenses and bring the rays to a point. Some of you might have done that already. And this diagram here is just showing that a lens works by effectively being a set of slightly different length prisms. Okay, so we know that light is refracted at a surface when it changes speed. Okay, so refraction is due to a change in speed of the ray of light. So as this ray of light enters the glass and crosses this boundary, there's a refraction. Remember, we've done this already. If you took a rectangular glass block and you shone light into that block, like this, as the light enters the block and crosses a boundary, the density of this material is different. And so this ray of light is going to change speed. And in this case, it will slow down. Okay? Remember, when we're doing anything about these optics, that we always say, what is happening to the angle relative to a line at right angles to the surface, which we call a normal. So this imaginary normal line is going to allow us to describe what happens during refraction. The incident ray of light entering the glass slows down, changes direction, and bends towards the normal. In other words, the angle that it's between the normal and the incident ray is larger than the angle here. And as the ray of light leaves the glass block, exactly the same thing happens. So we've got our imaginary normal line. Instead of going straight on, it's going to bend away from the normal, because the ray of light is going to speed up again. And if you remember, we talked about imagining a little car driving along the path of this light with its wheels on the corners. And as that car enters the glass, it would be like the car entering a muddy patch. One of the wheels slows down. This one. And that would cause the car to skid inwards and bend. Okay, so an easy way to remember refraction: when the light goes in, it bends in. And when it comes out, it bends out. Remember, those are relative to the normal line. So leaving the glass block, this angle is smaller than this angle. And mathematicians amongst you, lots of you will realize that this angle here will be equal to this angle here, just like this angle here will be equal to this angle here. These lines are parallel. So a lens works through refraction, and because the effective, this infinite stack of prisms are different thicknesses, and you've got less of an angle here, look, you get different amounts of bending, and they bring the light to this point that we call the principal focus. Okay, notice that this ray of light that's hitting the center of the lens, which is effectively a rectangular piece of glass right in the middle, the beam of light goes straight through without deviating, okay, because it has hit the surface at right angles and therefore won't change direction. It will change speed, okay? And in the exam, you often see rays, beams of light waves slow down if the speed changes, but the frequency is obviously staying the same. Then the wavelength would get smaller, and then when things speed up, the wavelength would get bigger again. Okay, so this would be like this wave. If it was a water wave, this would be the refraction would be caused by shallowness. So you've got deeper water with bigger wavelengths, shallow water, and then water getting deeper again. And you can see that if you sit on the beach and look at the waves are further apart out to sea and get closer together as they come up the beach where the water gets shallower. Okay, when they go out again, they get further apart in a deeper water. So refraction is caused by a change in speed. The change in speed can alter the wavelength. And if this was in water, water waves are slower in shallower water. Okay. Right, let's get back to lenses. So here's our diagrams from the book showing your convex lens, the principal focus, and the focal length, okay? And here's our diverging concave lens, just like the diagrams I've just drawn for you, okay? These lines are dotted because there is no light traveling here. Yeah, we're imagining that this is where they come to a point. It's like an imaginary beam of light. Okay, the solid lines show where light is actually moving. This would have been the experiment that we did. Okay, and we'd have found that the image formed by this converging lens. Okay, and we could use that to look at the features of images. Remember, images can be magnified or diminished, upright or upside down, inverted, and they can be formed on a screen, so that we'd be investigating real images here, or they can be virtual, right? And we would find that the fatter a lens is, the more it bends light. And so if you want a shorter focal length, a fat lens bends light more. That's a rubbish diagram. And you get a shorter focal length. Fat lens, more bending, closer focus. Okay, so we would have been doing this experiment with this lamp with a crosshair to form an image on a screen, and we can change the distance of the lens. So where the lens is relative to the object will determine the features of its image. Okay, right, from biology, you will already use this equation in a similar way when you look at microscopes. Magnification as a value is a ratio, and it's a ratio of how big the image is compared to how big the object is. So if you're using a lens, here, look at the relative positions here. The lens is far away from the object, the little bird on top of the tree here, yeah, and the tree itself. The image is smaller than 1. And here, look at the position of the lens. It's being used to magnify. Yeah, the image is larger than the object. The ratio is greater than 1. Right, so we can use this method to calculate magnification. Now, you are expected to be able to show how these images form using diagrams like this one here. Okay, it's quite hard for me to draw them well, but we're going to go through looking at this as an example. Okay, so notice that the lens has been replaced by a single line. Okay, and with these two little arrows on the end, that is telling you that this is a convex lens, and therefore is converging. It will bring light to a point on the object lens. It would look like this, a concave lens. Right, we'll come to this one in a minute. Most of the diagrams fit with convex lenses. If the object relative to the focal length of the lens will determine where the image forms. Okay, so keep this in mind, and I'm going to make a bit of space and draw a diagram down here. Okay, I can put my straight lines in. So in the exam, if we were doing the exam, you would get a diagram that's blank, like the one you've just seen, and there would be a principal axis a position of the lens. Let's show that it's a convex lens. And 1, 2, 3, 4, let's use 4 blocks. The focal length, 1, 2, 3, 4, and twice that. 1, 2, 3, 4, the focal length, and twice that. So any exam question with a grid or graph paper, the diagram can be to scale, okay? And when we start to draw our diagram, everything now is going to be to scale, and the set of instructions I'm going to show you, will work for every one of these diagrams that you follow. So let's imagine we've got an object here. Okay, I've drawn it as an arrow because we need to know which way up it is. So this object could be a tree. It's sitting there like that. Here's my lens. I know my lens is going to bring light to a point. Okay, so we're going to all the way, whoops, when we draw a straight line to the lens. It's a bit wonky. And we know that this is a convex lens, so it's converging. We continue that line diagonally through the focal point. Okay, yours will join up nicely here. So that's line. Second line from the top of the object, diagonally through the center here. Now those two lines are sufficient to give us where the image forms. We could draw a third line that would go through this focal point. And then along here. So let's draw the optional line in. I'm going to draw it in another color because you don't actually need it. So the third possible line would go through here, through the focal point here. And then, whoops. Dear, can I move this? It's all a bit glitchy and rubbish. Let's move that down a bit. Okay. So there's our third line. You can see that we don't cross is where this part of the object will be. So the tip of the arrow will be here. And my image will form here. Okay. If I was looking at this image, I would be seeing, look at the length of the arrow, a inverted, it's upside down, a diminished, it's smaller, and a real image because the light rays have passed through where the image forms. I'd be seeing a smaller upside down image of the tree, which I could project onto a screen. So this setup here would be like the arrangement of lenses in a camera. You're taking a photo of a distant object, and all of, let's imagine we're taking a landscape picture, all of those mountains are forming an image on the size of either your piece of film in your camera or the sensor that's in your digital camera. Okay, where the image forms depends on where the object is. Okay. Now, there's a few special situations, but what at some point when we finish this meet, I would try drawing this sort of diagram and then putting the object beyond 2F. I've shown you that one. Try putting the object between 2F and F, and try putting the object between F and the lens. Okay. You also get some special events where if you put the object at the focal point distance, some things happen. Okay, so you could try these different position objects from the lens. Right, let's go back up here. Okay, so this method, yeah, practice this. Draw to scale, otherwise it doesn't work. So either measure carefully where your F and 2F go, okay, and try different positions of where the object is. And I've put a YouTube video on today's assignment so that you can have a go at doing these drawings. If you've got some graph paper, that's brilliant. Okay, but you don't need to have graph paper. You can draw the lens and the principal axis. These distances must be measured carefully. Okay, and then your diagram will be to scale. Try different position between 2F and between F and the lens. Okay, remember this line is being brought down through the focal point of the lens. Now, if we were doing the same diagram for a convex lens, okay, bear with me. Everything is the same. Okay, so we're going to set up our principal axis. We're going to draw a line to represent the lens. We're going to show. I'm going to mark to scale the focal distances. Here, change color. Okay, we can going to draw a line from the top of the object to the lens. But we also know that this lens is diverging. Okay, so we're not going to draw a line down here because this is a diverging lens. We're going to draw the line spreading out, and we know where it spreads out because we know that the line, this part, this position here. Okay, I'm just going to draw the line and I'm going to move it if I can. Whoop. It's quite a challenge. Okay, so this should be, it's quite hard for me to draw. This should be going through the focus on this side. Okay, this would be a dotted line if we were doing it. I could show you properly. And then we'd have a line always that goes to the center of here. Okay, so you can see that these lines do not meet on this side of the lens. There's no way they can meet on this side of the lens. and the image forms where they cross, which is here. Okay, so this image is going to be at this point here. So we've got this special situation where we're looking with a diverging concave lens where the image forms on the same side of the lens as the object. Okay, so here we've got the object and we've got the image, and we can say that the image is upright, it's the right way up, it's diminished because it's small. Okay, concave lenses are used to correct short sight. Okay, concave lenses are used to correct short light. This image can never be projected onto a screen. Okay, think about what you've done in biology about the eye. When you look and you're short-sighted, yeah, your lens is focusing in front of your retina, so you need to spread the light out a bit more before your lens in your eye does its job, and then the lens in your eye is focusing the adjusted light onto the retina. Okay, so I need you to have a go. I need you to have a go at drawing these. Okay, this diagram is showing somebody looking through a convex lens, and here is the situation where the object is very close to the lens. Okay, and notice that the two lines here to the lens through the focus, diagonally through the middle, these lenses are spreading out. Okay, they're never going to meet, but we could imagine that they meet, and remember that's where the dotted lines meet here at the back. So in this special situation with a convex lens, okay, so it's still bringing light through the focal point. If the object is very close, then the image forms beyond where the object is and is magnified. So this is how a magnifying glass works. Think what happens when you look through a magnifying glass. When you look through a magnifying glass, you see a magnified image of the thing that you're looking at that is the right way up, bigger, and is on the same side of the lens as the object. Okay, so convex lenses are the ones we use for cameras, projectors, magnifying glasses, telescopes. Okay, the special example of a diverging lens, yeah, we're using to correct short sight. Right, as you go, note down some uses of the lenses as you move through the 2 pages I've directed you to. Okay, well, I feel like I've talked quite a lot. Are there any questions? If you've got any questions and you want to put them in the chat, then do. I will put the recording of this meeting and a printout of my screen in our assignment for today. And I want you to go to page 211 and have a go at those questions. Have a go at drawing these ray diagrams for yourself. You must use a ruler, okay? Otherwise, everything will go wrong and you won't get accurate answers. So unless you've got questions, leave the meet. Have a go at the questions on page 211. Upload me a photo of your work or a document. Okay, any questions, stay on the meet now or stick them in chat.
Thank you, sir.
You're welcome.
I have a question. Does it matter like how big proportionately you make the object?
No, it doesn't matter. If you're drawing it on squared paper, it will be to scale. So in the exam, they'll tend to draw the object for you, so it will already be done. If you're just drawing your own, I wouldn't go really big or really small, because it will make it difficult to measure, or you might not fit it onto your piece of paper. So I'd keep the focal lengths. It doesn't matter what they are, it matters that they're equally spaced, the f and the 2f. And then it doesn't matter how big the object is, because it could be any scale, couldn't it? So if you, I don't know, if you were looking at a skyscraper that was 50 meters high, you could make your line 1 centimeter or 5 or 10, it wouldn't matter. But appreciate that when you draw your diagram, the image will be to the same scale as your object that you've drawn. Does that make sense?
Yeah. Okay. Thanks.
Okay. Welcome, Lydia.
Hi, sir. My internet cut out a little bit when you were doing the diverging concave lens
Yeah.
towards the end. Could you just show me where each of the lines come from?
I will do. Yeah. Hang on. Let's go back. Can you still see my screen?
Yeah.
Yeah. Okay. So this is the diagram that you would have to draw if it was a concave lens, and so we know it would be concave because you've got these little oppositely shaped arrows on the ends, and so that's telling me that this ray of light here, let me get so I can draw again, this ray of light from the object to the lens, and then we know that it spreads out, and we know that it spreads out at an angle such that that ray of light, we imagine, passing through this focus on the same side of the lens as the object. Does that make sense? So there isn't really any light here.
Right.
Yeah. So if you imagine,
not sure.
So rather than in this diagram, imagining light, a ray going to the lens, and we know that it's that I draw to the lens will go through the focal point. Yeah. This one is like the neutral line that always goes through this central neutral point without being changing direction. And this is the same on the other side through the point. But if you look at our diagram for a diverging lens here, yeah, we explain where the focus is for the diverging lens, because this is the light hitting the lens and bending outwards. Yeah, hitting the lens and bending outwards, and these two virtually, yeah, we imagine them coming to a point here. Okay.
Okay. Right.
Right. So we know that this line, this construction line, when we draw it to show where the image forms, is going to pass through the principal focus, but on the same side of the lens as where the object that you're looking at is. Okay, so that's what I've shown here. Look, the ray of light spreads out, and I know which angle to spread this light out at, because I know that it will go through the focus on this side of the lens.
Right. Okay.
Yeah, but there's not really any light. There's not really light isn't passing through this point. Yeah, the light's doing that, but we're imagining that if it came to a point, it would be here.
Yeah, that makes sense. Thank you.
Does that make sense? And so this will always cross on the same side of the lens. So an easy thing to remember about concave lenses is the image is always on the same side as the object. It's always upright, it's always diminished, and it's always virtual. It doesn't matter where you put the object. Yeah, this is the image will form over here, because this ray of light will never cross this one. Does that make sense?
And I wasn't quite understanding the virtual thing with this one, because it looks like there's a ray of light going through the one of the sides, but
yes, this is like a construction line that we have to draw to explain where this image forms in the lens. Yeah, there's no
okay.
that you can use the definition of virtual here is we cannot project this image onto a screen. Okay, because the screen would be over here. Yeah. So when if you're wearing glasses and you've got these rays of light, so here's the lens in your eye, which is converging, and you're correcting your sight if you're short-sighted, yeah, by putting a lens in front of your eye, and this lens is going to spread the rays of light out a bit first, yeah, so that they come to a point further back than they would have done if you didn't have this.
Okay.
Right. So if you're wearing glasses, if you don't have your glasses on, this lens might focus your light here, and if your retina in your eye is here, everything will be blurry. So you correct your sight with this concave lens to spread the light out that's coming into your eye, so that when your lens does its job, effectively it's making this lens less powerful. It's making it bend the light at a bigger distance away from it. Does that make sense?
Yeah, and the questions that we're doing, are there answers for them, or do we just do the questions?
I'll share the answers with you tomorrow, or next lesson. And so your first task next lesson will be to purple pen these questions.
Okay.
So you won't get all that done now because I've talked for quite a long time. Okay, Josh.
Cool.
Yeah,
Thank you.
good to speak to you.
Have a good day.
You're welcome. And you.